Hi folks, in today's video we are going to be doing an introduction to nuclear chemistry. We're going to be looking at the three different types of radiation before moving on to how to understand nuclear reactions. So the stability of an atom depends really on the number of protons and neutrons in its nucleus. So most isotopes that are stable have kind of like a 1-to-1 ratio. However, isotopes have an unstable nuclei, they break up, or what's called decay. So radioactive decay is when an unstable nucleus loses energy by emitting radiation. So your lighter nuclei have roughly, as I said earlier, a 1-to-1 ratio of neutrons to protons. However, as they get more heavier, the number of neutrons increases. Therefore, that means they can make it a little bit more stable because they increase more rapidly than the number of protons, and that's how something can undergo what's called radioactive decay. We call these nuclei radioisotopes, and they are just simply isotopes which are radioactive. Unlike most chemical reactions where the reactions occur in the outer electrons, radioactive decay occurs in the nucleus, or the nuclei of those radioisotopes, which is entirely different from any other chemical reaction. Radioactive decay involves changes in the nuclei of atoms. So the radioisotopes give out radiation, and there's three types: alpha, beta or gamma radiation. Radioactivity or radioactive decay alters that neutron to proton ratio until the radioactive isotope turns into something that's a little bit more stable, so it forms another stable nuclei. There are three different types of radiation that we need to be aware of: alpha, beta and gamma radiation. So alpha radiation consists of two protons and neutrons, and it carries a 2 positive charge, or in other words, it's a helium ion. However, usually we just ignore the charge. Since it's positively charged, what that means is it'll go towards something of a negative charge. So for example, if we put it through a plate, it would go towards the negative plate. It can only travel around about a few centimetres, so alpha radiation can be stopped by just simply a piece of paper. Beta radiation is an electron which is ejected from the nucleus of your atom and can be represented by nothing for the mass number, a -1 for your atomic number, and a charge of -1, but again we tend to leave the charge out. Since it's the opposite of a helium or a alpha radiation, it can be attracted towards a positive plate because it has a negative charge. However, it is slightly more dangerous when it comes to stopping it. Instead of just a piece of paper, it can travel up to 1 metre, and you need something like aluminium, kind of a thin sheet, before you can stop beta radiation. Last but not least, we have gamma radiation. So gamma radiation is electromagnetic waves that are emitted from the nucleus of your atom. They can travel long distances and can be only stopped by thick barriers made of lead or concrete, and because they don't carry any charge with that electric field, so those positive plates, it would just go straight through them. So here we have that diagram of the three particles going through an electric field. If you have a look up the top, we can see we've got beta radiation that goes towards the positive plate because it's a negative charge. Then at the bottom we've got alpha radiation that goes towards the negative plate because alpha is positively charged. And then last but not least, we've got gamma radiation that goes right the way through because it has no charge, it's not deflected in any way. So here's a quick summary. We have alpha with the symbol, a mass of 4, charge of +2, beta and gamma, and we've got how alpha, beta and gamma radiation can be stopped. So we've got paper for alpha, thin sheet of aluminium for beta, and then thick concrete or lead for gamma radiation. So now we're going to move on to nuclear reactions. So a nuclear reaction is what happens when that alpha, beta or gamma radiation, well not really gamma radiation, is emitted. In a balanced nuclear equation, so the mass on the left hand side of the equation has to equal the total mass on the right hand side, and it's also same for the atomic number. So let's have a look at some examples. So here I have an example of alpha decay or alpha radiation where we have radon and it decays to polonium here. Now if you have a look, you can see we've got from 222 on the left hand side and we've got 218 on the right hand side, so we're missing 4. That's where we write the 4 for the helium. And then if we take a look at the atomic number, we've got 86 at the bottom, 84, that's the difference of 2. therefore we put the 2 at the bottom. That's how you know it's alpha decay, because it's got a difference in 2 in the atomic number and 4 in the mass number. With beta decay, it's a little different. The atomic number on the right hand side is actually going to increase because your beta radiation has an atomic number of -1. So let's have a look at the top here. We've got radon again, 228 to 228. That's not changed at all. But at the bottom, we went from 88 up to 89. So we've increased by 1 on this side. So the only way we can balance it out is by doing that -1 for that beta radiation. And that's how you recognise it's a beta radiation, because the atomic number on the right hand side is actually increased. With gamma radiation, it won't have any effect on the mass or the charge. However, there are 2 other examples of things that can be in radionuclear equations, and they are protons, which can be represented by a 1 for the atomic number and the mass number for a proton, and then 1 for the atomic number, 1 for the mass number, and 0 for the atomic number for your neutron. Here we have some examples to do. So we've identified Y, R, Z. So again, if we have a look at the first one, we went from 222 to 218, so I've got a difference of 4 at the top. And then if you have a look at the bottom, we went from 88 to 86, so we've got a difference of 2. That must be your helium, or sometimes you can write the alpha radiation like this. If we have a look at Z, the top's not changed, so it's 228 to 228. However, the atomic number is actually increased, so we'll have to do a -1. Therefore, we know that's the electron, which sometimes we can write as this for your beta radiation. That was just a quick insight to radioactivity, the 3 different types of radiation, before going on to look at alpha, beta decay in nuclear equations.